Hello, welcome everybody to the second METALLICO webinar on how reactors for leaching and bioleaching are working, insights from research to practice. I'm very happy that you joined us today. So my name is Ramona Simon, I'm from DEKIMA. We are partners in METALLICO, and together with my colleague Joanna Malarz, we are responsible for the communication and dissemination in METALLICO, and we are very happy to have you here today. So before we start the webinar, we will give you some technical hints. So today we will listen to 7 different speakers, and if you have questions to them, please use the Q&A tool. It's above in the menu. So if you have a question during the talk, you can put your questions there. The reason we use the chat today is you are muted, you can't speak. So this is how you can address your questions to each speakers. Please also make sure that we know which speakers you refer to, that you put the name of the speakers in front of your question. So, yes, let me start with our first speaker of today. It's Dr. Andrzej Chmielarz.
Hello.
Hello. He's the head of Hydrometallurgy Research Group, where he is since 1970 in Łukasiewicz-IMN. He is an expert in hydrometallurgy and environmental protection. His scientific achievements are mostly focused on waste valorization by hydrometallurgical methods and upgrading of the basic hydrometallurgical processes. He will give in his presentation an overview of leaching types in hydrometallurgy, fundamental technologies, advantages, and challenges. I'm very happy to hear you talk. You can
Thank you, Ramona, for introducing me. Ladies and gentlemen, my name is Andrzej Chmielarz. I am an employee of the Institute of Non-Ferrous Metals in Poland. When somebody asks me about my profession, I'm most willing to answer I'm a hydrometallurgist. Today, I've got the honor of giving an introductory speech to kick off our webinar on leaching and bioleaching and leaching and bioleaching equipment. But as usual, before we get to the meritum of the speech, let's think a little about what hydrometallurgy is. According to the definition that I once dared to formulate myself, hydrometallurgy is a method of obtaining metals from primary and secondary raw materials by dissolving them, purifying the solution obtained, and the metal recovery in elemental form or as chemical compound. We all know that hydrometallurgy is situated as a field of metallurgy next to pyrometallurgy. Hydrometallurgy, currently defined, includes several areas of basic and applied research. The first, we will today be talking mainly is extraction or leaching and recovery of metals from primary and secondary raw materials. Next is separation of solution components via different techniques like IX, SX, precipitation, crystallization, membrane techniques, etc. Next area is electrochemistry in aqueous solutions, organic solutions, and molten salts. Purification of waste solution with techniques of environmental remediation. are included in the hydrometallurgy too, and very important mass production of metal salts and corrosion in aquatic environment. Of the technique mentioned here, leaching is special because it occupies the basic place. So let's go back to the definition for a moment and try to define the definition of leaching. Leaching is the operation of dissolution of solid raw materials in a liquid phase due to chemical reaction between components of solvent and raw materials. I think that there are two very important properties or parameters of in this definition. The first is that we have to have the two-phase materials, solid and liquid, and chemical reaction must proceed between these components. Leaching can be carried out in under different conditions. Under normal pressure, and when it is called atmospheric leaching, or elevated pressure and temperature, and we are calling it hydrothermal leaching. You can do it underground on a heap in tank reactors, leaching tanks or autoclaves, in acidic or alkaline, oxidizing, non-oxidizing, or much less often reductive environment, in the presence of active in the process living cultures, mainly bacteria or fungi, and in this time we've got process which is called bioleaching. And leaching can be performed in a continuous or periodic manner. Leaching, like any other technological process, is described by a group of technical parameters. They are composition of raw material and the leaching medium, ratio of solid to liquid phases during leaching, or the concentration of the slurry, temperature and pressure, leaching time, which is sometimes called retention time, and description of other hydrodynamic conditions. The result of the leaching is usually determined by composition of the obtained solution, unsolved residue and off-gases, leaching efficiency of the essential components of raw material, leaching bars, unit consumption of reactants, energy, and so on. So let's go to the basic leaching method, starting with leaching on the heap. This technique is commonly used in production of copper from oxide type copper ores, and you can see on the left the diagram simplified of the operation. Raw material is built in a form of heap after crushing in agglomeration. Lixiviant solution is applied from upper side, and pregnant solution is received from the bottom side. Sometimes air is pumped through the heat, especially when bioprocesses takes a significant part in the whole leaching process. On the right, you see the picture of the only one European plant which works according technology of heap leaching. You can see on the right the heaps and what I must to underline that heap leaching process takes plenty of time. The first leaching is normally is carried out around 1 to 1.5 years. After this period, because there is still too much of valuable metals in a material, the heap is found the second time on the other place, and leaching continues. Next, the most popular tank leaching. Leaching is carried out in the simple vessels which are equipped with steered agitator. Sometimes this vessel is equipped with cooling or heating jacket, and the buffers inside to improve hydrodynamics inside the reactor. On the picture on the right, you can see a view of Cabrera's Cruces plant, which is one of the full hydrometallurgical plant, the second in Europe. Or the technology is based on the tank leaching. You can see on the picture here a set of tank reactors. As I remember, it is 8 volumes of 300 cubic meters. Very interesting and technically not so easy to be designed and afterward performed is a process which needs three-phase reaction. It means that we've got in the reactor, within the reactor, we've got solid materials, leaching liquor, and the third gaseous phase. It is usually oxygen, air, or the mixture of air and oxygen. Here we've got tank which is used in so-called Albion process. What is interesting in it is this nozzle in which, through which gas is transported into the tank with the over sound velocity. And on the right side, you've got the next possible construction, which is very similar to the flotation cell with aerator, through which air is added to the reaction mixture. This type of reactors are constructed in our institute, and they were, for example, industrially implemented to oxide liquid coming from sodium desulfurization plant. Next, we've got tanks, which were used to build the line for cobalt recovery from cobaltous slag in Kasese in Uganda. It's an example of biometallurgical process, which was invented by our colleagues from BHGM, France. And finally, hydrothermal leaching. Hydrothermal leaching, the heart of hydrothermal leaching is always autoclave. Here you've got the horizontal drum autoclave in which process takes place from the upper side. Raw material and liquid is pumped to the autoclave. From the bottom, oxygen is oxidative agent, and steam for heating and to keep the proper pressure are delivered. On the slide, you've got very interesting figure. It illustrates which type of autoclave high pressure processes are used in metallurgy of non-ferrous metals. The highest pressure and temperature is used for process which is called hot pressure acid leaching, and is used for nickel recovery from laterite type ore. Next one, pressure oxidation process is usually implemented in gold industry for the kind refractory gold ore, which means that the main phase of the ore is pyrite, and before oxidation and gold and leaching of gold, this pyrite must be removed from the raw materials. Next area is area of temperature and pressure to treat battery. Chemicals, mainly I think black mass, Next, it's matter leaching, oxidation, iron precipitation, and anode slime processing in the lowest part of temperature and pressures. And finally, as I said on the beginning, leaching tanks are used for batches, but if you arrange them in a series...
Short interruption. Maybe if we could come to an end quite soon. This
yes,
would be
yes,
very
yes,
great.
yes.
Thank you.
Two slides. And if you arrange it in a row, you can produce plenty of solution. This type is implemented mainly in zinc electro winning. And last slide on advantages and challenges for hydrometallurgy and leaching. As advantages, we can say that hydrometallurgy is high, but not always satisfactory. Kinetics of leaching and leaching efficiency. Leaching tanks are relatively simple in construction, especially those who are operating under atmospheric pressure. There is virtually a very high limit of volume of leaching tanks, up to 1,000 cubic meters. In leaching tanks, we can conduct three-phase redox processes. And what is very important, it is possible of using polymer plastic as a structural material for reaction, even for temperature over 100 degrees Celsius. And finally, challenges for hydrometallurgy and leaching process. The first is, in my opinion, reduction of cost of preparing the material for leaching. I mean about crushing, grinding, and so on. New designs of agitated and aerators are needed to minimize energy consumption, as well development of high pressure, high temperature leaching. And finally, we need, and it is, I think, the problem of the scale of the world. It's development of method to reduce the discharge of solution of simple organic salts from wastewater treatment plants. This problem is the bottleneck even now, and can become a factor that significantly limits and sometimes eliminates the use of hydrometallurgical technology at all. Thank you very much for your attention.
Thank you very much for your talk. And now we want to proceed. So if you have questions to Dr. Andrzej, please put them into the chat. So later in the Q&A, we have the chance to answer them. But now we can already see Joanna Malarz coming up the screen. She can already start sharing her screen. She's a specialist at Łukasiewicz. She's working at a hydrometallurgy center. Her research focuses primarily on the chemistry of cobalt, nickel, copper, rhenium, zinc, and precious metals. She specializes in hydrometallurgical processes, including material leaching, selective metal precipitation, and ion exchange techniques. So today she will present the latest results from METALLICO, and her presentation will be about sustainable and safe iron arsenium alloy leaching. So welcome, and the stage is yours.
Thanks. Good morning, ladies and gentlemen. I will present our work on the sustainable and safe leaching of the iron arsenic alloy with a particular focus on controlling the toxic gas emission generated during the process. The iron arsenic alloy is especially important because in addition to iron and arsenic, it contains valuable critical metals that can be recovered and reused. However, the presence of arsenic means the material must be processed careful and under control condition. The Koni process allows the recovery of cobalt, nickel, and copper from iron arsenic alloy, which is a waste product from a lead pyrometallurgical production. The process begins with crushing the alloy to reduce particle size, followed by leaching to dissolve the metals. Iron and arsenic are precipitated as scorodite, while the remaining amounts are removed as iron concentrate. Finally, copper is recovered as copper carbonate and cobalt and nickel as cobalt nickel carbonate concentrate. The iron arsenic alloy is polymetallic material composed mainly of iron and arsenic. A typical contains about 40 to 55% iron and 25 to 35% arsenic. Because it's high arsenic content, this alloy is classified as hazardous waste and is usually deposited on the designed industrial landfills. The alloy used in our research contained about 55% arsenic and 24% iron, as well around 7% copper, 2.6% cobalt, and less than 2% nickel. The main components of the alloy occur in metallic form. Because the material contains arsenic, the laboratory scale leaching experiments also included monitoring of arsenic concentration during the process. You can see a condition. You can see on this slide the leaching of condition. During the experiments, the arsenic concentration in the gas absorbing solution was measured to evaluated potential emission. In both tests, arsenic concentration didn't exist 0.5 milligrams per cubic decimeter. Based on the laboratory results, the next step was the development of a pilot scale installation. The Łukasiewicz-IMN Institute supervisor built construction and operation of the pilot plant at its facility. Same modernization of the installation was required to perform the pilot experiments. The most important upgrade was the purchase and installation of new reactor, along with all necessary equipment. The pilot plant has a capacity of 1 kilogram per day. When selecting the material for the pilot scale reactor, it was important to ensure high resistance to abrasion, high temperatures, and strongly acidic environments. Two materials were considered: acid resistance stainless steel, such as 316L, and a duplex alloy, for example, grade 2205. They were compared in terms of mechanical strength and corrosion resistance under the expected process condition. Due to its significantly better corrosion resistance and mechanical durability, the duplex alloy was chosen for the reactor components in direct contact with alloy and the leaching mixture. A new reactor with a volume 1 cubic meters made a duplex alloy was construction and successfully integrated with the existing infrastructure at Łukasiewicz-IMN.
So for the next speaker is already appearing here. So yeah, I'd like to welcome Dr. Ben Wilson. He is today here from the European Respect Project. So I'm very happy to welcome this sister project here. So to his persona, he's a senior scientist of raw materials, metallurgy and electrochemistry based in the School of Chemical Engineering at Aalto University, Finland. Their research is in the area of hydrometallurgy, corrosion materials, and he is currently devoted to recycling and waste valorization. The main aim is to understand, develop, and optimize industrially scalable processes that have reduced environmental impacts and produce minimal waste for more sustainable real-world solutions. So I'm very happy that you are here. Okay,
Thank you very much, Ramona. Hopefully you can see my slides.
We can see it and hear you well.
Okay, excellent. Well, so greetings from the Respect Project. So this is a European project for a competitive, circular and sustainable European battery manufacturing industry. So today I'm going to give you a very quick overview of one small part of the work that we've been carrying out on this project related to the hydrometallurgical recycling, so black mass leaching performance, a combined experimental and regression modeling approach. So, I mean, there's quite a lot of targets from the Respect project, but the main one to be considering today is looking at the recovery of these critical raw materials or critical metals from battery waste, from black mass, so cobalt, manganese, nickel, graphite and lithium. So yeah, the idea of the Respect project is actually to try and exceed the levels set by the European Union for 2031. So we're trying to get to those levels already and thinking about, you know, producing material that's ready for recycling and trying to reach the recycling efficiencies. So we're talking about hydrometallurgy here. So this is, as was explained very nicely in the first two presentations, this is atmospheric on a lab scale. So 1 litre jacketed glass reaction vessel. There's temperature control via a water bath through the sort of outside there. There's a 4-blade PTFE impeller. So it's got a 5 centimetre diameter and a 45-degree angle. So providing the agitation that's quite critical for these kind of things. And in this case, the stirring, the agitation was provided overhead with a 300 RPM speed. So what does that look like in reality? Well, you can see it there on the left. There's some black mass in there. We're being leached by 2 molar sulfuric acid, so our lixiviant. It's an industrial black mass, so that's from lithium-ion batteries, so NMC111, so nickel, manganese, cobalt, all in relatively equal proportions. The critical thing that was mentioned as well, the solid-liquid ratio. So the ratio we were using here was 200 grams per litre, which is more reflective of the industrial levels of solid-to-liquid ratios. And the actual material itself had a combination of lithium, cobalt, nickel, manganese, but also copper and aluminium and iron. So the last three particularly come from either the casings or the electrode materials, which are also within the battery elements, not just the active materials which contain the lithium, cobalt, nickel and manganese. So part of this was to look at the process as a whole, but to try and look at what difference can the addition of reductants take part. And we had a nice highlight there from Joanna, sort of talking about the use of peroxide. But peroxide itself can be quite expensive and has a well-known sort of high carbon footprint associated with its manufacturing process. So we tried to look at alternative reductions, in this case iron sulfate, but also looking at copper as well that's recovered from the battery electrodes, and also trying to exploit some of these materials, the copper, aluminium and iron, which is already within the black mass, so we don't have to add so much reductive material. So the first thing that we looked at was the effect of temperature on the black mass leaching. So this is without any reductive agents added. This is just looking at temperature and the leaching lixiviant of sulfuric acid. So as you can see here, as the temperature increases, not surprisingly, you start to see high yields of the critical metals, thinking about the manganese, nickel, cobalt particularly. So yeah, temperature has an effect. And actually at 70 degrees, we found that we had yields above 90% for the target metals. However, 70 degrees can be considered relatively high temperature for industrial operation. So we tried to look at ways to reduce the temperature whilst trying to maintain the leaching yields. Was that possible? So use of reductants, hydrogen peroxide, as I say, is the one that's currently has wide application in industry, but we're trying to look at whether copper, iron, aluminium could have an impact as well. So why these alternative reductants? Well, in fact, most of these NMC have, some of it's quite easy to leach in the first instance, just with the regular acid, but some components of the NMC crystal structure are actually quite hard to break down. So the idea of using the peroxide as an extra oxidative agent, but actually the use of iron in conjunction with copper and aluminium can provide a reductive process as well due to this electron shuttling between the iron and the copper and the aluminium. So you can get some electron transfer, which causes the oxidation and reduction process to be enhanced compared to without the presence of these metals. So this is just a quick overview of the kind of materials that we were looking at. So how did we approach this? Well, we took a design of experiments approach, also known as DOE in short form. So for those of you who don't know, this is actually a statistical tool. So it allows you to assess the interaction of different effects on, between multiple variables. It's based on regression modeling, and it's used to construct models that, in this case, was looking at predicting leaching yields from our industrial black mass. So the parameters we selected for this investigation included temperature, the concentration of the iron, not just was already in the black mass, but what we added in terms of the iron sulfide and sulfate, and also the additions of copper and aluminium or peroxide. And then the models were fitted with a partial least squares model. And you can design the sort of experimental protocol. There's programs to help you design this, so you can have different experiments with different levels of iron or copper and peroxide, and this provides you the information to base your statistical model on afterwards. So just a quick example, as we've not got a lot of time today. So just thinking about what we saw at 30 degrees without any reductants, the levels of leaching of the key metals was relatively low. But as you can see here, even at 30 degrees with the addition of iron reductant at 0.4 grams per litre or 0.6 grams per litre, there's been an increase in the leaching of the the metals of interest, still relatively conservative, 50-60% for cobalt, for example, but this is still an improvement in the at a temperature of 30 degrees compared to without any reductant whatsoever. But as you can see, once again, once we increase the temperature to 50 degrees, there's an increase in the amount of leaching yield or recovery of the metals into the pregnant leach solution that start to reach more appreciable levels up towards 90, the targets that we have there. So that was just a quick snapshot of the data. Of course, we had a lot more data if we think about the table of experiments that was listed there on one of the previous slides. But it was clear from our results that temperature is the most impactful factor for all the elements, thinking about cobalt, nickel, manganese and lithium in this case. And temperature was found to be especially key for lithium. And these graphics here show the sort of impact of each individual parameter on the yields based on the statistical analysis. But it's clear also that the addition of copper and iron have a significant effect on the final leaching based on the statistical analysis. In fact, interestingly enough, peroxide has less of an impact when compared to the addition of iron and copper, but peroxide was found to be quite important for actually the leaching of cobalt, so the cobalt yields. But such predictions are subject to small errors due to the black mass inhomogeneity. Of course, black mass, it's normally in this case was 111, but it comes from different sort of input streams. So in fact, it can be, the amount of material in each yield varies somewhat based on that. But what kind of results could we get out? Well, we can do some contour plots. This is for cobalt at 1350 degrees, where we have copper and peroxide as the variables. In this case, the temperature was 30 degrees and the iron level was quite low at only 2 grams per litre. So as you can see here on the left, the lines are almost diagonal. We have peroxide there on the left axis and copper amount along the right axis. And these are kind of like at a 45-degree angle. So that would suggest, when comparing copper versus peroxide, that the copper and peroxide have similar impact on the leaching yields, at least after 2 hours at 30 degrees. Whereas if we look at 50 degrees in this case, you start to see that there is a change from the 45-degree angle towards more vertical. So this would mean that the peroxide addition has actually, at this temperature, has only a weak impact on the leaching yields. So it's actually the copper which is the additions that's having the most impact rather than the peroxide. And this is not a surprise, as higher temperature is known to decrease the relative efficiency of hydrogen peroxide as a reductant. So you increase the temperature, actually the peroxide can break down rather than break down during the reduction of the cobalt or the NMC. It can actually just break down due to the temperature effects as well. So just to finish with some quick conclusions. I mean, it's possible. We showed that you can make statistical models for the cobalt, nickel and manganese yields based on temperature, iron and copper as variables, and also peroxide. These models indicate that copper additions could be more beneficial for improving the yields recoveries compared to peroxide, particularly at higher temperatures. And it also shows that the metal impurities within the black mass can be used as a reductive agent rather than adding peroxide. So in fact, you can then start to reduce the carbon footprint and also be able to exploit some of these impurities within your black mass. So we're able to, look at these models as a way of performing leaching performance predictions. So we can now this is based on NMC 111, but once as you can see from this sort of equations we now have based on the models, it is possible to take an NMC, maybe 532, for example, and then calculate based on the different temperatures that would be appropriate for leaching, what kind of yields would be applicable from this new material based on the models. So a quick tour there for you about the RESPECT project, but if you have any questions, of course, we'll be happy to answer them later. Thank you very much.
Yes, thank you also very much for this very interesting presentation. In the meantime, we can proceed with Mateusz Krzyszewski, so then you can hold your presentation now. So maybe I give a short introduction to you. You can share already your slides. So you received your PhD in 2014, and since 2015 you are working in the Łukasiewicz Institute of Non-Ferrous Metals. You are currently the head of research group and of hydrometallurgical processes and upscaling. You are mostly concerned with hydrometallurgical technologies for lead, zinc, bismuth, and antimony recovery, as well as arsenic sequestration. I'm very happy that you are here today with the head of the TETA-led European project, and yeah, very exciting to your talk.
So thanks a lot for introduction. Hello and good afternoon to all of you. I would just shortly, let's say, comment about, let's say, somehow recently finished EU project that was realized in cooperation with some partners from Nordic countries as well. The acronym was TETA-led, so hydrometallurgical recovery of lead from sulfate-rich residue. So, is problem or not? Yeah, it's not. So, general description: what was the problem and how we solve it? So, generally, there's some significant amount of the leaching residue that are produced and that contain some significant amount of lead, and this leaching residues from the, in our case, from the zinc industry, are either disposed or landfilled in some case, or it can be also processed by the lead smelters, but it involves some, let's say, additional fees concerning the transportation of the quite heavy and moisture-containing materials. So the objective was to develop technology that can somehow face this problem and recover this lead. We used the, let's say, so-called desulfurization method, which allowed to, let's say, energy consumption to diminish negative impact of the, let's say, emissions of toxic gases. So our magic substance was TETA, that is a triethylene tetraamine, which is quite powerful extracting agent, quite, or maybe not quite, very powerful and very, let's say, selective toward lead sulfate. So another, let's say, lead compounds are quite inactive, but for lead sulfate, it allows water amine solution allows to extract lead sulfate to liquid phase, to aqueous phase. Another thing is that this technology is quite recyclable, and for maybe some of you who are closer to polymers and so on, TETA or triethylene tetraamine or mix of other alkyl amine solution is a popular hardener for the epoxy resin. So that's general idea. If it's possible, if we find that lead in this zinc leach residue, in our case, is in the lead sulfate, or generally other materials that possess lead sulfate in it, can be treated with TETA solution. This is some, let's say, photos from our lab scale experiments. So of course, grinding analysis and so on, and drying and so on. But generally, of course, we did it also in the pilot scale, and I will just show you how it looks like. The general technology for recovery of lead. So if you have shale, in our case was super hot acid leaching from one of the smelter from Europe. First is the leaching using amine water solution. So the lead sulfate is extracted to liquid phase. Then we have filtration. So let's say other materials is left. Then carbonation. If you purge gas CO2 through this solution containing amine with lead sulfate, a molecule, you will obtain lead carbonate, which is the main product of the technology. In this step, you have a quite big amount of CO2 that is, let's say, dissolved in the solution. So the best idea to remove it from the solution is just acidify it with some amount of sulfuric acid. So you have desorption of the CO2. And the last step, quite challenging, but also very positive for the whole technology, is the removal of excessive sulfate ion, which allows to, let's say, regenerate triethylene tetramine's water solution, which can be used for another leaching operation. So carbonation in case of the lab scale was also done in the flotation machine with a proper volumetric flow rate of carbon dioxide. Of course, in the pilot scale, it was done not in the beaker, but it's in a big 3 cubic meter reactor. Of course, in lab scale, we did it after every 15 minutes. The filtrate was checked whether whether lead ions are still present. So that's why we found at what pH practically this depletion of lead ions is, let's say, finished. Then quality of morphology and quality of this lead carbonate is quite important. So as you can see, 75% of lead was present in this first, let's say, lead concentrate. In fact, it was quite pure lead carbonate. And the regeneration scheme is based on the, let's say, main reaction tank, which is supplied with the solution after carbonation and after precipitation of lead carbonate. So this solution with some increased amount of sulfuric acid passes to the reactor. From another side, you have by peristaltic pump calcium hydroxide pump with a proper, of course, residence time. This calcium hydroxide is done as a suspension, and you have a continuous collecting of the regenerated theta solution. So we have came up with all these parameters for the process. So the time, the temperature, and so on, the acceleration as well, and it allows us to perform let's say, to pass from the lab scale to pilot scale installation. As you can see, there are, let's say, main 4 reactors. It was done in our premises in the IMN, Institute of Ferrous Metals. So the leaching reactor for the shallow leaching, carbonation reactor for purging CO2, the, let's say, biggest one, the 3.5 cubic meter. Acidification, just to add acid, sulfuric acid concentrated to dissolve and evolve carbon dioxide. And the last one, steam heated by a heating mantle, the 4th reactor for the regeneration, so for production gypsum and to regenerate theta, so it can be recycled to the beginning of the process. Of course, IBC containers for any buffer solutions and so on was there. In every operation, it was maybe let's say this image is quite small, but generally we use like semi-industrial filter presses containing a number of plates, so chamber plates, filter press. And from time to time, there is an additional, let's say, zinc removal or zinc retraction operation that should be performed. So shortly conclusions about, this technology with amine allowed us to recover 90% of the lead from this super hot acid leaching. This triethylene water solution can be successfully applied for other, let's say, materials, solid materials containing lead sulfate. Technology allows to produce pure or high quality lead carbonate, and that can be used for smelting. It was also done in our case. So our colleagues from pyrometallurgy department made some close to 1 ton of the lead carbonate was smelted for produced lead. Amine regeneration has to be performed with acidification, that is for sure and must be. We also propose some membrane technique to remove some excess of water that can be done during recirculation, during continuous operation, when you have some, let's say, income of the or some water is fed because of filtration, because of washing filter cakes and so on. And the last thing, that any zinc that can be somehow accumulated during, let's say, operation of the amine technology can be periodically eliminated, and this technology for this elimination was also developed in IMN as a sparingly soluble salt was done. So probably it was quite short, but thanks all of you for listening, and if you have any question, please. Thanks a lot.
Thank you very much for this nice presentation. We would now go into the Q&A block for all the leaching presentations. As we are running a little bit out of time, I plan to have 5 minutes for that. And for the discussion, I want to welcome the chair of the discussion, Andrzej. I would be very happy to give the word to you now. Are you here? Welcome.
Here
Yes.
I'm
Yes.
in answer and questions. I've noticed one question which is connected with foam, which normally is generated during the leaching, and how to fight with foam. And I know two methods. One, the first is to add anti-foaming chemicals which are produced and can be bought on the market. And second, which I prefer, is to destroy the foam with the high pressure streams of water, which are direct on the surface of the foam via nozzles which are mounted on the inner side of the tank. So this is my answer to the question I've noticed.
We have another one from Nestor. He's asking a question to Ben. When you mentioned that aluminium and copper have been tested as reductants, do you mean that they were intentionally added, or are you referring to the fractions? Originating.
So thank you for the question. Now, in this case, depending on the black mass you have, there tends to be always some copper or aluminium and iron in there, depending on how it's been processed. Iron's quite easy to remove with magnetic means, but in this case, we already had some copper and aluminium in the material, but then we added also some additional copper from electrode materials. So these were also recovered electrodes, and we, tuned the copper in this case to the levels that we were investigating. But it is a good question. There is some discussion at the moment which says, okay, what we can try and remove all these impurity metals, copper, aluminium in particular, but it can be quite energy intensive. So the idea behind our system to try and sort of reduce the carbon footprint, reduce the energy requirements, actually exploit the level of copper and aluminium also in the material as well. But it depends on each black mass is different, so the levels are different. So in our case, this was actually quite low in these materials, so that allowed us to add to sort of change the level to a desired controllable level. But it's a good question. But typically, it's trying to exploit the materials that are already in the black mass.
Okay, wonderful. I hope the question is answered. Maybe the last question of this Q&A round goes to Mateusz. Here is a question which is in the precipitation of lead carbonate, did you face any problem with the filtration of the crystals? Did you have the chance to measure the particle size of the precipitate?
Regarding the lead carbonate, no problems with filtration. The particle, I mean, we did the PSD analysis of the material. I don't remember the right number now in my head, but generally this was quite easy as most of the lead materials, and it wasn't. If I expect that the question was, it wasn't let's say too fine particles. So we haven't observed any problems for the chamber filter presses.
Perfect. And maybe one last one. There's the question of the recovery of theta. It was also in the chat asked. Do you have quickly a number to your hand?
The acid consumption for process, or?
The question just says the recovery rate of theta.
No, at this point. I mean, if you want, you can just write me an email, but no, not from my head, just shortly. No.
Okay, that's fine. Numbers are always complicated to remember.
Yeah.
Yes, so thank you very much again for all the insights into the leaching, from the fundamentals to the special things which is occurring in all the projects. We are now going over to the bioleaching part, and my colleague Jana will guide you through this.